Okay. Okay. So today, okay. Let me just remind you, in case you forgot, what we talked about last time. So last time I spent quite a bit of time talking about gravitational collapse because I think it underlies a lot of this development that went into ultimately ended up being black hole thermodynamics. And then I reviewed the laws of black hole mechanics that were shown to bear a very striking analogy to the laws of thermodynamics. So if you remember, there was a zeros law. Maybe somebody can tell me what the zeros law was. Hello?
That was associated to the surface gravity being positive, being greater than zero. Yeah.
Being constant.
Constant, yeah, sorry.
Yeah. So it was indeed related to the surface gravity being constant on the Killing horizon. So this is not something that we proved, and in order for it to be constant, it's really important that the horizon is a Killing horizon, which people in the 70s they showed that stationarity, the horizons of stationary black holes are of this Killing type, so they're normal to a Killing vector. So I should say I didn't have time to go through all the technicalities of the derivation because that would be like a very long course. But I strongly encourage you to go to some of the reviews that are available all over the place and look at these derivations. So for example, for this I can recommend the Townsend review from around 97, but you also have Walt, for example. He can tell you where all the literature is and so on. Okay, very good. So the zeros law is that the surface gravity is constant on the horizon of a stationary black hole, and that of course looks like the zeros law of thermodynamics, that at equilibrium the temperature is constant. The first law, can someone else tell me what the first law is about?
It gives the change in area due to the change in mass and change in angular moment, or the conserved charges, the change in conserved charges.
Exactly. It relates the change in the area of the horizon with precisely this factor of the surface gravity influence to the change in mass minus omega delta J plus whatever other terms you might have if you have a charged black hole. And this is basically, so this law, as I was trying to show, this is derived using Einstein's equations. So especially in the physical process derivation that I tried to present towards the end, you see very explicitly that you write the area in terms of this, the change in the expansion. You use Ray-Choudhury's equation, and in the Ray-Choudhury equation, you trade the Ricci tensor for the stress tensor using Einstein's equations, and then you get precisely this law. Okay, it tells you how the horizon geometry adjusts in response to the passage of mass and angular momentum. For people who are interested, I'm not going to go into this, but there's some very nice work by Jacobson. I forgot when. I would say mid-90s. Okay, I really don't remember when. On the converse of the first law, trying to show that if the first law is satisfied, as you'd expect in a thermodynamic system, then the Einstein equation should be thought of as an equation of state. Okay. If anybody's interested, I can look for the reference. This is the Jacobson. Okay, finally. And the second law. So can somebody tell me what the second law was saying?
It was about assigning the black hole a particular entropy and then saying that generalized entropy is always greater than or equal to zero. The change in generalized entropy.
Okay, very good. So you want to say, so yeah, so first, there's assigning the black hole. So the second law of black hole mechanics is just the fact that delta A is 0 in classical processes. Then if you want to talk about entropy and talk about this generalized entropy that Bekenstein introduced, which is the sum of the area with an appropriate coefficient plus the entropy of matter, that should increase in any process. So I should say that this area increase is just a classical fact. Quantum mechanically, it is violated. So, for example, so I presented this, and then these laws look like just like analogies in the beginning, but then Hawking discovered that actually black holes emit black body radiation at a temperature k bar h over 2 pi. Right? This is the Hawking temperature. And then black holes can evaporate. In the evaporation process, obviously, the area of the black hole shrinks. So how is this possible? Any idea?
Is it because it is losing its mass away in the form of the black body radiation?
Yeah. So basically, yeah. So we had shown we had shown in the previous class that the area of the horizon was always increasing, and in order to show that, remember we used Raychaudhuri's equation, which is just some geometrical fact, and the null energy condition for matter. Remember? Right? So in the Raychaudhuri equation, we're replacing R mu nu, K mu, K nu, whatever those vectors were, by T mu nu, K mu, K nu. And then we're using the null energy condition to say that that term was positive. Do people remember this? Yes, okay, very good. I should look at the chat. Okay, so basically it's that condition that's being violated quantum mechanically. So the null energy condition, it's a condition that holds very, it's reasonable to assume it holds for classical fields, but quantum mechanically is violated. And this is how the Hawking evaporation process can actually reduce the area of the event horizon. On the other hand, the generalized entropy that Bekenstein introduced, which is the entropy of the outside matter plus area of the horizon, and then you can put the correct constants. This object actually increases because even if this term decreases in the evaporation process, the outside radiation contains all the Hawking quanta that are being emitted, and actually this has more entropy than is being lost. Okay? So the generalized entropy, even in the quantum Hawking evaporation process, the generalized entropy does increase. Okay. So and then what we concluded with was the fact that the fact that the physical temperature of the black hole is given by this Hawking temperature. It physically emits thermal particles and so on, implies that this object should really be thought as a physical entropy of the black hole that should be assigned to the black hole, and it's called the Bekenstein-Hawking entropy. Okay? And before I go on, let me just ask if there are any questions about these black hole thermodynamics issues.
Yeah, so about the zeroth law, what is playing here the role of thermodynamical equilibrium? How does it being a killing horizon play into the whole equilibrium bit?
Right. Yeah. So what people were asking was, what is the final equilibrium state? So at equilibrium, you're no longer time dependent, right? So this is why they were looking for static or stationary solutions, because once you're in equilibrium, you don't move anymore. And then as I was trying to explain the history, they were very shocked to find out that the only static solutions had to be spherically symmetric, had to be the Schwarzschild black holes, and the only stationary solutions had to be axisymmetric and had to be the Kerr black hole. But the equilibrium is basically the stationarity. I mean, the reason that I'm not reviewing these theorems is that they're incredibly technical. This is mathematical physics, so I don't want to go into like deep technicalities. And I don't know, but for example, if you look at Walt's review of black hole thermodynamics, it's in Living Reviews in General Relativity. You can find all the precise statements of what is being proven.
Yeah, no, thank you. That was clear. Thank you.
But yeah, so it's equilibrium is basically the stationarity of the black hole, which implies that it has a killing horizon. And once you have a killing horizon, then you use your favorite formula for K in terms of C dot C blah 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 squared, and then you start proving that that actually that thing is constant using the fact that it's normal to a killing vector. That's essentially the proof. Any other questions?
On the same lines, how does it correspond to, like, in thermodynamics, the third law, as per the third law of black hole mechanics, it says that it is impossible to reach kappa equals to 0 in finite number of steps. So, like, what corresponding steps are we talking about here?
Yeah, I mean, people have discussed this law quite a bit. How to say? I don't find it very physical. Yeah, so you can ask. So black holes with T equal to 0 are the so-called extremal black holes. So you can have extremal Kerr, where you take so Kerr for a given, in order to not have a naked singularity in Kerr, you need something like G m squared greater than J. Okay, and the extremal limit is when this is an equality, and okay, and that black hole, if you naively compute its temperature, it has exactly 0 temperature. You can come up with a Reisner-Nordstrom black hole, so that's the charged black hole, or a Kerr-Newman black hole, which has both charge and angular momentum, and you have similar lower bounds on the mass in terms of the charge. Or charge and angular momentum, and those naively have 0 Hawking temperature. So people try to show that you can never reach exact extremality in a finite number of steps, and there's some papers in the all the literature, I think Wald, and I mean I can get the references if you want. More recently, there were some mathematicians trying to disprove the third law by trying to create an exactly extremal Reisner-Nordstrom black hole from a collapse situation. So I said that under generic initial conditions, gravitational collapse will lead to the formation of a black hole. So okay, collapse leads to singularities. The question is whether singularity is going to be behind the horizon or not. And cosmic censorship says that under generic initial condition, it's going to be hidden by a horizon. However, if you fine-tune your initial conditions, you can actually end up with a naked singularity. And I think this is what some mathematicians were playing with, I think last year. And they tried to make an exactly extreme Reisner-Nordstrom black hole out of collapse in a finite time, which would seem to violate the third law. And I haven't fully followed what was happening, but then I think Harvey Rial was writing papers that, I don't know, the setup was not very physically motivated, and they had some fields that were violating I don't know what, so this is not a very good setup. So it's not clear to me. Okay, I haven't followed, but also it's not clear to me that whether that's a proper counterexample or not. But the reason that I don't find this discussion terribly physical about extremal black hole very physical is that there have been very beautiful works in the past 5 years or so by people like Luca Iliescu from Berkeley, or Gustavo Turiac, who showed that actually when you look at very near extremal black hole, including full extremality, you have very large quantum corrections to the geometry. So the classical gravity approximation is not valid. So discussing, how you can reach exact extremality doesn't seem to make physical sense. except perhaps for supersymmetric black holes. But for non-supersymmetric ones, it doesn't seem to make sense. So to me, it's not clear what the status of this third law is supposed to be. But I haven't fully followed the discussion.
I see. That clears it up. Thank you.
Yeah, why supersymmetric makes sense?
Sorry, what? Can you speak up?
Why supersymmetric makes sense? If you can explain a bit.
Yeah. So this is really beautiful. I think Luca Iliescu gave a talk at Strings 22 about this, which was a really beautiful talk, but I'm sure you can find many more talks online, or you can invite him, or Daniel can invite him to give lectures in the school. I think that he's a fantastic lecturer also. Or maybe Gustavo, who's Argentinian. So basically what's happening is that you have these very large quantum corrections, and in the non-supersymmetric case, they basically wash out. So normally you'd think that, for example, this extremal Kerr black hole has a finite entropy proportional to J at exactly 0 temperature. However, what they showed is that that's false. And actually, the density of states does go to 0 due to these quantum corrections when you go at very, very low temperatures, temperatures below, I think, something like 1/J to the 3/2. Okay? In the case of supersymmetric black holes, what happens is that you have some additional, this going to 0 of the entropy happens because of some zero modes, and the zero mode counting is different for supersymmetric black holes, and there's some cancellation. So actually, you can still have a non-trivial finite entropy at extremality. So what they were saying is that for non-extremal black holes, if you look at the density of states, so you have something. So the naive as a function of the energy. So this is the naive curve that it would be. This is naive. What you get from classical gravity. What they're saying is that for non-supersymmetric, it goes like this. And for supersymmetric, it sort of goes like this. There's a gap, and then you have a large density of states at extremality. But this is far more advanced than my course. But it's really beautiful. If you're interested, you should either watch the talks or read the lectures. It's very nice. But this is basically the reason I don't really want to talk about the third law, because I think extremal black holes should be treated with care, and one cannot just do naive classical GR in that case. And any more questions?
Just one last bit. Sorry, Monica. I mean, when you were addressing the fact that when you change, when you are addressing the second law and you have that when we are in a quantum regime, this null energy condition is violated, right? Am I misunderstanding that is because of that fact that you can introduce H bar in the formulas of the entropy of the black hole? No, doesn't come from that, right?
No. So the H bar, okay, sorry. Yeah, so this is the classical, analogy, right? This is what you can show just using classical black hole mechanics. This is what Hawking and company did in 74, whereas Hawking radiation was, I think, in 76. So basically what Hawking showed in 76 was that, and this is an effect that's just there for, accelerated observers in Minkowski space, and you don't even need a complicated black hole to show it. So basically what happens is that if you have different observers which have different time, then what might look like the notion of particle for these observers would be different. So for example, if you just have empty Minkowski space, so the vacuum of Minkowski space, which to a standard, inertial Minkowski observer just looks empty, the Minkowski vacuum. If you consider an accelerated observer in Minkowski, which only sees half of the spacetime because it comes in and then it has to go out because it's accelerating, that's a so-called Rindar observer, that guy is going to see the Minkowski vacuum as if it were terminally populated. And it's precisely this effect, which is called the Unruh effect, which is happening in the black hole situation, where the role of the inertial observer, the inertial Minkowski observer, is played by the observer that's falling freely through the black hole horizon, who doesn't see anything. He doesn't notice that there's a horizon there or anything. And the role of the accelerated observer is played by those observers that go along the orbits of the Schwarzschild killing time, the DT. And these are accelerated observers because they stay at, they stay outside the horizon, so they have to accelerate. And it's basically because of this. Accelerated observers see this infalling vacuum, which is analogous to the Minkowski vacuum, as being thermally populated, and you can compute this temperature. All you're doing is just quantum field theory. Okay, in the Minkowski's case, it's not even in curved spacetime. In the black hole case, okay, you have to do curved spacetime, and it's a quantum effect. So this is where the H bar is coming from. The H bar is coming from the fact you're doing this perturbative quantum field theory calculation, and you find that the temperature is proportional to H bar. And now, if you try to separate this term into kh bar over 2 pi times the rest, you see that you're going to get 1 over 4 pi g h bar. Now you want to take this term and put it in the area to say that's the entropy, because you want to get the first one. This is where it's coming from.
I understand. Okay, so in the end, it's
Yeah.
because
So if you want to know more, you should look in some textbook for the Unruh effect, and the Unruh effect is going to explain this H bar factor in front of you.
Got it. Thank you.
Yeah. So it's really important. It's a quantum effect. This black hole emitting thermal radiation. This is why these guys were confused in the beginning. Classically, the black hole doesn't emit anything, but it's important. It's a quantum effect, and then it starts. Okay, maybe I should actually start today's lecture, which was supposed to be long. Okay, very good. So what did I want to say? So today I'm going to talk about holography, and which, as I was saying in the first lecture, has been motivated by black hole thermodynamics. Okay. Basically by this formula that Becker-Stein-Hawking entropy. And as you see, this formula right now, it doesn't have any statistical interpretation. One isn't counting anything. One is assigning to a black hole that's characterized by just 1 or 2 numbers, like mass and angular momentum. It's assigning this number, which, as we were discussing last time, it's a really huge number. It's 1 degree of freedom per Planck size area of the horizon. This is a huge number, but you don't have any statistical interpretation for it from the point of view of the spacetime you started with. That statistical interpretation actually came much later. It came in the mid-90s with the work of Strominger and Rafa and ICTP. And we're going to discuss a bit more like that. But right now there's no such thing. However, one can nonetheless assume that this number does have some sort of meaningful microscopic interpretation as some number of degrees of freedom of the theory of the black hole, and then see where one gets to. And so the first statement, so I'm going to make a number of vague statements, which are going to end up with some sort of amazing conclusion. So this S black hole is like area of the horizon divided by the Planck length squared, as you can see from here. And because the entropy is proportional to the area, it looks like the degrees of freedom they make up the black hole, whatever they are, they live on the surface of the black hole. That's just from scaling. So as we discussed, so this is this number is a huge number for a large black hole. However, because the entropy is just proportional to the area and not the volume, one would imagine that it's very easy to come up with some matter configuration, like standard matter, that has entropy proportional to volume, and make that thing have more entropy than the black hole entropy in some region of given size. Okay? And sort of the first statement is that actually that's not possible. So if I give you some region, some finite region of space-time R, and I'm going to take it to be spherical with size r. So I'm not going to be super precise. Then the black hole, taking its entropy seriously, is the most entropic object one can fit. And the reason that matter that has volumic entropy cannot have more entropy than the black hole that only has entropy proportional to the surface area is that entropy doesn't just depend on size, it also depends on energy. And in order to make the matter have more entropy than the black hole, you have to give it so much energy, then that is going to grow outside of its Schwarzschild radius and is going to collapse to a black hole. So it's because of gravitational collapse that this statement is true. So let me just do a little calculation. So let's model the matter by some finite temperature gas. So matter, I just take it to be some gas at some finite temperature T. And then at sort of high temperatures, there's no other scale in the problem, so I can just do some dimensional estimates. So I estimate the energy of the gas. So it's going to be proportional to the volume, because this is some local thing. And by dimensional analysis, I'm going to get a T to the 4 over here. Temperature has dimensions of energy, of mass. So this is T to the 4 cubed. Whereas the entropy of the gas, which is dimensionless, it's going to be V, and then I need to put a T cubed. So this is TR cubed. Okay? So now I want that the entropy of the gas is larger than the entropy of the black hole that fits inside the entire region. That is as big as my entire region of radius r. Question: what's the entropy of this black hole? Can somebody tell me?
It has
4
to be
pi r
something
square
like
over
r squared.
4gh bar.
Okay, very good. Thank you very much. That's very precise. So I'm going to set pi to 1, 4 to 1, and h bar to 1. So it's just going to be r squared over g. Okay? So far, so good. But, okay. As I was saying, in order to be able to talk about the gas, I should make sure that, so I'm having some gas in some finite radius. I should make sure that this gas doesn't undergo gravitational collapse. And the condition for the gas to not undergo gravitational collapse is that the size r be larger than the Schwarzschild radius of the gas associated to this energy, which is how much? What's the Schwarzschild radius of the gas of energy?
2gm.
Very good. I'm going to set 2 equal to 1, so it's just G times T gas. Okay? Okay, so this implies that G times T to the 4 r squared smaller than 1, which implies that T is smaller than 1 over r squared G to the 1/4. And in turn, so now if I compute the entropy of the gas, it's going to be smaller than T cubed times TR cubed. So T times R, the R, I put it in here, becomes to the 4th. So this is going to be R squared over G to the 3/4. Okay, I just plugged in this one. Okay, which is just the area of the region divided by G to the 3/4. So you see this is much, much smaller than the black hole entropy at radius r, because I'm assuming that the r is much greater than 1. Okay, so this is a calculation shows you that just ordinary matter, because of its possibility of undergoing gravitational collapse to a black hole, generically, as we showed, it's never going to have more entropy than a black hole that actually fills the entire region. Okay. And so hopefully the argument is clear. And given this, you know, Toft in '93 had a really bold proposal. He basically said, well then, that basically means that the degrees of freedom of quantum gravity in my region are, okay, I mean, it is true. So the conclusion of this little exercise is that whatever standard matter I put in here, or whatever black hole I put in here, it's all going to have less degrees of freedom than the black hole that fills the region. The black holes that fills the region, I can think of it as having its degrees of freedom living on the surface of the region, and therefore, basically, he's saying anything that may be happening inside this region, you know, little people living under the sun and looking at black holes or whatever, is describable by degrees of freedom that live entirely on the boundary of the region R. Okay? So that concept, so the fact that you can encode everything that goes inside this bulk region by degrees of freedom that live on the boundary is called holography. And it's a truly drastic proposal about the behavior of quantum gravity. It basically says that, you know, if we look at the true degrees of freedom of quantum gravity, you know, we might think that the quantum gravity, you know, in our world is going to live in 3+1 dimensions, but actually this proposal is saying that no, actually it's going to live in 2+1 or whatever. You don't have enough degrees of freedom in your theory of gravity to make up for a local theory in that number of dimensions, but only for a theory in a lower number of dimensions. Okay, so for this reason, the Toft paper is called dimensional reduction in quantum gravity. It says that fundamentally, the full quantum theory of gravity is fundamentally lower dimensional than the classical limit would seem to indicate. Is this clear?
Can you please repeat the statement once?
Yeah. So the statement actually. So this whole thing is very vague. So did you understand the story about the black hole that fills the region has more entropy than anything else that I may be putting inside this region, any sort of ordinary matter? Is that argument clear?
Yeah.
Okay, so from there, since it says that since the black hole has, you know, I can think of it as having its degrees of freedom distributed on the surface because it has entropy proportional to the area. So I can think there's, you know, 1 degree of freedom per Planck size area of the surface. This is the black hole that fills the region. And since the black hole has more entropy than anything else, it means that also anything else can be described by the same degrees of freedom that live on the boundary. It's basically saying, had I had, for example, if I had a proper local theory in the bulk, then its number of degrees of freedom would really scale like the volume. However, in a gravitational theory, because of this collapse business, the total number of degrees of freedom of the gravitational theory, assuming that black holes carry this much entropy, is actually that of a local theory that lives just on the boundary of the region. It's effectively one-dimensionless. It doesn't scale like the volume. The maximum number of degrees of freedom doesn't scale like the volume of the region. It really scales like the area. And that's a very, very drastic behavior. Because it means that the whatever theory of quantum gravity is an incredibly non-local theory at sort of low scales. Okay, so that's the implication, and so this proposal, yeah, indeed, it's very drastic because of that. Because if you really think as your the way that holography is usually stated, it's stated as saying that a theory of quantum gravity in some region R or in some space-time can be rewritten in terms of a non-gravitational theory that lives on the boundary of the space-time. It's not 100% clear to me that's very generally true, but in the examples that are known of holography, it is true. You can rewrite a gravitational theory in higher dimensions in terms of a non-gravitational theory in lower dimensions. And it's also like what's very drastic. What's very drastic is that, so if your fundamental theory is really this theory on the boundary, which counts the correct number of degrees of freedom of your theory, it implies that so this direction, this radial direction, is sort of emergent. It's some sort of illusory direction. It also implies that the locality that one sees in this direction, I reminded that we live in a theory with gravity, so this argument in principle applies to us. The locality of quantum fields that we see in a theory of gravity can at best be approximate. Like fundamentally, it doesn't exist in the theory because the theory fundamentally is not a local theory in the bulk, but can at most be a local theory on this boundary. So everything is very drastic here, and it also this holographic business is also intimately related to the black hole information paradox that I briefly mentioned at the end of the last lecture, which was supposed to be this clash between you know, gravity, smoothness of the horizon, and so on, and between general relativity, let's say, and quantum mechanics in the process of black hole evaporation. But you know, all of that argument in a sort of hidden way uses locality in the black hole space-time. But as we see in holography, which is supposed to be a general thing, locality is very badly violated. So that this probably has to do very much with the resolution of the black hole paradox, which, you know, there's been progress, but not enough to actually understand. Okay, so this is basically Toft's argument that gravity is holographic. As you see, it's a very, very general argument because it just uses black holes, gravitational collapse, very fundamental properties of gravity. At the same time, you see that it's an incredibly vague statement. Like, it doesn't tell you what this theory is, how it acts, how can you check. It doesn't tell you anything, but it really has this nice universal flavor. So in the rest of the lecture, I wanted to actually start doing some proper holography by giving you, one precise example. So the reason that people, work so much on holography nowadays is because a few years after this proposal, there came out a concrete holographic correspondence by Mandasena, the so-called IPFT correspondence, where you can actually check that this is happening very concretely in specific examples. Okay, so now I'm going to move to IPFT. Are there any questions about the general argument? But the general argument indicates that this holography, it's supposed to work in general spacetimes, although it doesn't tell us how and why, but it's really supposed to work beyond this. Are there any questions about this? Everything clear? Sorry, guys, you should speak up rather than, because I don't see the chat very well. So why in the case of black hole? Yeah, okay. So please, the next time you should just ask me these questions, because I don't normally look at the chat. Why in the case of black hole, the thermodynamic entropy depends on the area of the black hole instead of the volume? This is what we derived last time. So as I was saying, this was a proposal by Begelstein, trying to salvage the second law of thermodynamics, which looked like it would be badly violated if you take some entropic object and then you put inside the black hole, and then suddenly all information about the object, its entropy disappear. So he was trying to salvage it, and then he came up with this entropy proposal because it sounded like a natural thing that's actually increasing. And I think also remember I mentioned the Penrose process, where you take a Kerr black hole and there's some process where you can extract the energy from the black hole, yet the area of the event horizon increases. So it's because it sounded like it was like sort of the natural proposal to be having, because this area of the event horizon was the quantity appearing everywhere in all this, area theorem. It was one could easily prove that it was increasing, and one could check this proposal. Is it particular for black holes in general, for any gravitational system? Sorry, the fact that entropy is proportional to the area, is that the question? So this is very particular for black holes, like a normal matter system that's described by some local gas, local quantum field. Okay. Of course, we should all be doing, if we forget about gravity, we should all be doing quantum field theory. And quantum field theory is just some local theory, 1 degree of freedom per space-time point, and so on, Planck size, whatever. So yeah, it's incredibly different. The black hole entropy, the fact it's proportional to area and not volume, is incredibly different from how normal matter behaves. And that's sort of the whole point of the discussion. So that's very good that you pointed it out. Does that mean quantum field theory lives in the boundary? It depends how general you want to be. So I try to present this 12th argument to the full extent of its vagueness. It's a very vague argument. Okay, it just says that you have enough degrees of freedom, and those degrees of freedom are as if you imagine them on the boundary of the region. Doesn't mean that they live on the boundary of the region. That just means that there are as many as you would have degrees of freedom by putting one per Planck size. But it doesn't tell you what they live. It also doesn't tell you that in general you're going to have a quantum field theory. So actually, if okay, given the pace, I'm not sure I'm going to end up with my fancy TTbar speculations. But in the fancy TTbar speculation, what's happening is that you have an example of holography, where the space-time is not ADS, it's something else. And the theory on the boundary, it's a non-gravitational theory. So that's in the spirit of holography. However, it's not a quantum field theory. It's a string theory that doesn't have gravity in it. So usually string theory has gravity in it, but that string theory, which is called little string theory, is decoupled from gravity. It's a very special kind of thing. So it's not really a theory of quantum fields, it's a theory of strings that lives on the boundary. So it doesn't have to be a quantum field theory. To me, in general, it's not even clear you can do this full rewriting, but those arguments suggest it. Guys, would you mind just asking the questions live? It's much easier for me. So does the thermodynamical entropy become entanglement entropy for the case of black hole somewhere? That's a very good question. So I wrote this generalized entropy formula, which was S out. So this is the Begelstein, right? Plus area of the horizon by okay, so this is the generalized entropy, and you can wonder what is exactly this matter entropy outside the black hole. So some people Actually, I think in the beginning, they were even trying to interpret black hole entropy like that. They try to say, or you can think of the matter entropy as entanglement entropy of the matter fields across the black hole horizon. I'm saying this statement for those people who know entanglement entropy, and I'm assuming the person who asked this question knows what's entanglement entropy. So you can think of this guy as entanglement entropy for the quantum fields outside the black hole horizon. Is that okay? And then you may get yourself into a puzzle because, as you know, in order to regulate that entanglement entropy is divergent. So in order to compute it, if this is the horizon, you basically have to put some sort of brick wall, you have to put some cutoff just outside the horizon, and this entanglement entropy diverges with that cutoff. Okay, so this part is divergent. As it turns out, those divergences can actually be absorbed into some renormalization of Newton's constant. So there's some work by Susskind and collaborators, and I think it's been made precise over the years. So at the end of the day, what happens is that none of these things are particularly well defined. But if you take the sum, this ambiguity is sort of cancelled between the two, and the total is supposed to be, yeah. So indeed, this piece is supposed to be thought of as entanglement entropy. There have been proposals or I don't know, I think it's probably true, but okay. So there have been ideas in the literature that this term can be thought of some sort of entanglement associated to edge modes when you split your space-time across the horizon, if you know what those are. But this is very advanced, I think. Okay, so if there are no more questions, let me just move on to talk about ADSC. Okay, so the people, the reason that people really love this IPFT correspondence is that it's a very precise realization of this holographic principle of the holographic correspondence, and is derived. It's actually derived. So this crazy idea of thoughts is actually, you know, it gets a lot of me. Derived within string theory. Okay, so in order to properly understand what I'm going to be saying in the next, for the rest of the lecture, I think you really need to take a course on string theory and understand these things well. It's well implemented there, but okay, I'll just try to say a few vague things and hope that they will make sense to you. Okay, so what is does anybody know what string theory is? Okay, let me test.
Yeah.
Yes.
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 So it's like
Oh.
basically
Can you say what it is? Maybe that isn't clear.
Oh,
a
okay.
theory where the fundamental objects are not particles anymore, they are extended objects called strings. Sheets
Very good,
instead of
very
word
good.
lines.
Okay, so now you got the definition of string theory. Very good. So indeed, so the fundamental objects are the strings, and there's some. So if you look at them, so these are some strings that propagate into some ambient spacetime, which is normally called target space. In superstring theory, for it to make sense, the target space has to be 10-dimensional. And from the target space point of view, the vibrations of the string look like an infinite tower of particles of ever increasing masses in units of something that's called 1 over alpha prime. So alpha prime has units of length squared. It's sometimes called the string length squared. Okay, and then there's some number. Okay, very good. So if you're at energies, there are also massless states in string theory, like you know, the graviton, some scalar called the dilaton, and so on. If you stay at energies much slower than this string scale, so normally we take the string scale to be very small, you only see the massless fields. And where I said, as I said, you have Jimmy and some other stuff. The string theory also has some coupling constant. Which is called G string. It's actually the expectation value of some scalar, and it measures the strength of string interactions. Okay, so basically, if you want string perturbation theory, to make sense, you need this G string to if G string is not small, then you don't have control over the theory, because one doesn't know of a non-perturbative definition of the theory. Okay, so string theory is better than, say, classical gravity and so on, in the sense that you have a description of this entire tower of states, so you can do more. You can go at energy scales of or the G string and still say something, and the theory has a lot of nice properties, you know. It resolves with divergences and so on. However, you don't have a non-perturbative definition of the theory. Very good. And what else? Another thing that string theory has, it's actually, it looks like a theory of strings, only in this weakly coupled limit, but it actually contains also non-perturbative objects, such as membranes of all sorts. D branes, NS5 branes, and then, okay, you can also go to theory. And these guys are non-perturbative because their tension goes like 1 over G string times alpha prime to whatever, you know, dimensionful number you need to add. Okay, so they're on 1 over G string squared. Okay, so you see that they're very, very heavy at weak coupling, but of course, if you want to strong coupling, fluctuate over. Okay, good. So now you know enough for me to be able to derive string theory for you. So the derivation of this ICTP correspondence, as I hinted a little bit in the introduction. So I think I'll. Okay, I think I did have something to say. Okay, this is not a very successful. There you go. And now you don't see it because I have to bring it to this side. So the derivation of the ICTP correspondence that one does in string theory, you basically start by looking at the stack. So the most famous instance of ICTP is the one that's obtained for the so-called D3 branes. So you're thinking about three-dimensional membranes that are some of the objects that you have in string theory. So you take n of those. So they're D3. So these are three-dimensional membranes embedded in 10-dimensional spacetime. Okay, and these membranes, okay, they have some gauge fields living on them, and actually at low energies, the theory that lives on these D3 branes is just a gauge theory. It's SUN super Young-Mills. So this is a non-abelian generalization of electromagnetism. It's called n equal to 4. This has to do with the fact that it's a supersymmetric theory. Okay, some important detail, but you don't need to know about it. Okay, so it's just some gauge theory in 4 dimensions. But of course, this is just at low energies. The full theory that describes the D3 branes are plus higher order terms that involves all these field strengths that involve derivative couplings and couplings to the bulk. So in the bulk, you might have gravitons, you might have all the other crap that lives in string theory. They're in principle there. However, when you go to very low energies, all these other couplings to the bulk and higher derivative corrections to this n equal to 4 spiral mills go away, and you're just left with this theory, which is a really beautiful theory, and moreover, it's a conformative theory, which are interpolars. Okay, so this is one side of the course. Okay, so it starts from this D3 branes, and here the low energy is very important in actually getting these theories. Otherwise, it's something very, very complicated, and that's coupled to the 10 dimension. So now, the point for deriving the correspondence is that these objects called D branes. So this is the description that in terms of this Yang-Mills theory is the description that they have at so-called weak coupling. Okay, so when G string is very small, and actually in the case of ND3 branes, the relevant coupling is the so-called Toft coupling, which is G Yang-Mills squared times the number of branes. Okay, the n from the SU. Actually, this is the Toft coupling defined for an SU. Okay, and this is equal also to G string times n in terms of the string. Okay, so this description is valid when this lambda is weak. As it turns out, when you go to strong coupling, the same objects are believed, or it's well-established conjecture, to have a very different description in terms of a geometry. So basically, you can think of these D3 branes as back-reacting on the metric and creating some sort of black brane solution of 10-dimensional supergravity. Okay, and this solution is described by some metric, which is very simple. It's 1 over square root of some harmonic function minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. Okay, plus square root of the same h of r times flat space, orthogonal flat space, basically, r squared d omega s5 squared. Okay, so what's happening? You're having a 3-dimensional object in 10 dimensions, in 10 space-time dimensions. So that's like in 9 plus 1 dimensions, if you wish. So that's like having a point object in 6 spatial dimensions plus time. Okay? Right? So a point object in 6 spatial dimensions is surrounded by a 5 sphere, which is why this 5-dimensional sphere metric is appearing over here. Okay, and otherwise I'm just saying, so I'm just taking a metric which is the same, so I'm preserving sort of Lorentz invariance along the brane directions, because so these are the 4 directions along the membrane, and this is just the transverse test. Okay, so this is just the solution. You back react this object that has now become heavy. It's one of these heavy membranes that I was talking about, and you get this metric where h of r, if you know string theory and so on, is given by, in terms of the constants of the theory, it's given by something like this. Okay, so basically what's happening when you're taking this very low energy limit, so you're having the same, this system which has these two different descriptions. Okay, I should say, so I mentioned this description is good at weak coupling. This description, if you look at it, is actually valid at strong coupling. And you can see because, how should we do it? You can look at sort of small distances. So when you see that when R is becoming small, you can drop the 1 over here, and this guy just gives you becomes square root of G string and alpha prime divided by R squared, which goes away with this R squared. So basically, you can see that you're getting the radius of the sphere squared is going to be square root of G string and alpha prime, where I said alpha prime is the string length squared. So basically, if you want your, gravity approximation to be valid, so not to be seeing, little vibrating strings, but actually only see the massless modes, you basically want that the size of this sphere that you're getting is much, much larger than the size of the string, okay? So you basically want, so you see the size of the sphere is proportional to the size of the string with this factor over here. So you basically want this factor to be much, much larger than 1, but you see this factor is nothing but the lambda. Okay? So these two descriptions are really in opposite limits of this coupling, of this Toft coupling lambda. They're valid, they have non-overlapping regions of validity. Another thing that you can require, or you can check over here, is that you want, in order for the gravity solution to be reliable, you also want, the characteristic size of the solution, which will take to be this radius of the S5, to be much larger than the Planck length. Okay, this is basically telling that you can ignore corrections from quantum gravity, which you definitely, since you know nothing about quantum gravity, you want to do that. And if you look at L Planck turns out to be, L Planck squared is square root of G string times L string squared. Sorry, do you see? Is it better?
Yeah, now it is.
Okay, so basically, by asking the characteristic size of your geometry, this say the size of the S5 is much larger than L Planck, what is it telling me?
LS has to be small.
It's telling, sorry, can you repeat?
String length has to be small. So if GS is much larger than P.
Wait, so I want this guy to be much smaller than the size of the S5, which is square root of GSN times LS squared. So what am I deducing from here?
I guess that the product of the G string coupling constant times N is much greater than just G.
N has to be large.
Exactly. So you see, most of these things cancel out, and what I'm getting is N has to be much larger than 1. Quantum gravity corrections down. Okay. Simple algebra. So this is very important because quantum gravity is really something that you cannot control even in string theory. So you want to be in a regime where the characteristic scale of your solution that you don't need to involve quantum gravity corrections, and that's the requirement that the curvature. So yeah, this L S5 is measuring the curvature of the solution. Roughly speaking, has to be much larger. The curvature of the solution, which is this one, has to be much larger than the Planck square, for which I give you the formula, and you deduce that you have to have a very large number of membranes. You have to have a very large charge. That's important. If you want to also not have to care about stringy corrections, which is something that sometimes you do have control of in string theory, then and you only want to do gravity, then you should just require that this lambda, which is proportional to G string n to some power, you want it to be. Okay, so this is the setup. So basically, one looks at this correspondence in the so-called Toft limit. Well, let me not mention the Toft limit right now. But anyways, you in order to trust these pictures, you need to take n very large and lambda fixed. Okay, so basically the argument goes something like this. You have these objects. At weak coupling, they look like this. At strong coupling, they look like that. Now I'm taking a low energy limit, and this low energy limit, what I'm getting on this side, I'm getting basically this SUN super young means theory on the T3 brains, and actually plus some free gravitons that float around in the bulk and don't interact with the brains. And on this side, at very, very low energies, well, I'm getting the free gravitons again in the asymptotically flat part of the spacetime that I don't really care about. I can just cancel them on both sides. And then I get contributions from objects that, okay, so this, when, so these are some sort of extremal brane solutions. They're like a bit like extremal black holes. So they have a very, very, very long throat. And down this throat, you have a very, very large redshift parameter. So basically, things that have finite energy in the throat because of this very large redshift are going to be looking like zero energy, close to zero energy from the outside. Okay? And those things survive. And because this is the same system on both sides, you come to the conclusion that n equal to 4 super young means, you know, SUN, whatever, d equal to 4. This theory over here is the same as string theory. It's actually called type 2B string theory on whatever background is living deep inside this throat over here. And if you're trying to look at deep inside the throat, that's the region where R goes to 0. So you can drop this one factor. And then what happens over here, you see, so as I argued already, you're going to get a sphere, a 5-dimensional sphere of this radius. And then you're going to get something that looks like a constant times dr squared over r squared. Well, you're going to get a metric. This metric is going to be minus dt squared plus dx, say vector squared plus dr squared. No, so I'm being stupid. This times r squared plus dr squared over r squared. Something like that. I hope you see from these terms plus this term in the metric and taking the limit on the harmonic function. And this geometry is known as HDS5. Okay? So the conclusion that you come with is that this n equal to 4 super young means, which is a 4-dimensional theory, which is a gauge theory, a bit like quantum commodynamics, is exactly the same as type 2B string theory, which is a gravitational theory that lives in 10 dimensions on this ADS5 times S5 mass. Okay? Of course, you have to do this properly. So if you want to learn this, there's this review that I'm sure you know by Magoo. So Aharoni, Upser, Maldacena, Oguri, and Oz that explains this very well. You can also look at Maldacena's original paper, but I think it's better explained in the review. So, but this is the basic argument. So please note that this conclusion is really striking, because it's telling you that two theories that live in different number of dimensions and look incredibly different. One is a gauge theory, one is a gravitational theory, one in 4D, one in 10D. It's telling you that they're actually the same theory. So this is a very, very non-trivial statement. How is it possible to have this non-trivial statement? It's basically because, the reason that you don't get a contradiction is because, as I was discussing, the regimes of validity of the Young-Mills description, where you understand it, where you can understand it perturbatively, is exactly disjoint, completely opposite from the regime where the gravitational description is weakly coupled. Okay, this was this discussion about lambda. So this is what we call a strong-weak coupling duality. So you have these two theories. These two things are supposed to be different descriptions of the same theory. When one description is weakly coupled, so I'm supposed to be fixing. I'm supposed to be fixing this n parameter, the number of branes. Let me take it to be large, just to be for things to be a bit better, and lambda small. So let me take n large to start with, and take the Toft coupling to be small. So that's the coupling of the gauge theory. So now I can do perturbative calculations in gauge theory. What happens on the gravity side is that, as we're seeing from here, you see? As we're seeing from here, when this Toft coupling, which is G string n, is very small, then the size of the S5 is comparable to the string scale. So that means that I don't have a nice, notion of classical gravity. I really have to study full string theory on my background. Okay, so which is very hard. Which is very hard. In principle, it's possible, but in practice, it's very, very hard. Okay. Whereas in the opposite regime, where the gravity description is weakly coupled, so where this string n is very large, then what happens is that the super Young-Mills theory is in the strong coupling regime, and it's basically impossible to compute. The number of diagrams is huge and so on. Okay? So this is known as a strong-weak coupling duality. It has some advantages and some disadvantages. The disadvantage is that it's very hard to prove the conjecture, because if you can compute here, you cannot compute here, and vice versa, so it's hard to test things. Normally, people test for observables that are supposed to be independent of the coupling, such as supersymmetric observables. However, one advantage of it is that it also, the strong-weak business is also making the conjecture useful, in the sense that you can use the weakly coupled gravity description to do calculations that otherwise you couldn't even dream of doing at strong coupling in a field theory. And this is indeed one of the ways that this correspondence has been used a lot. And you might have heard of IDS-CMT, IDS-CD, and so on. So people do use it quite a bit in order to get insight into strongly coupled dynamics of quantum field theories. Okay, so what I said so far was at a very large n, because I don't want to deal with quantum corrections on the gravity side. And of course, this derivation that I mentioned, it's only valid in the larger limit, because the gravity side only makes sense then. However, it's very interesting to think. So the strong form of the ADS-CFT conjecture is that it's valid for any n and G string. And in that case, so I told you, so at finite n being the ratio of the curvature of the geometry to the Planck scale, finite n means that you're in presence of quantum gravity corrections. So this is a regime that you'd really love to understand, and we have currently no means, even string theory cannot do it. So what this duality says is that you could in principle be using the gauge theory side, the super Young-Mills, which makes perfect sense at finite n, to be defining what you mean by quantum gravity in ABS 5 times. times S5. And this is another truly interesting possible application of the correspondence and why people are interested in it. So as I said, one of them is that you can model strongly coupled field theories using weakly coupled gravity. That's something very successful. Something a bit less successful is doing the other thing, understanding quantum gravity through the correspondence at finite N. It's a bit harder, but it's clearly one of the main avenues of research to try to understand these things. Okay, we skipped the polls as far as I say. So I wanted to say a couple more things before I go into details. I'm sorry, I'm going very slowly. So what shall we do? Shall I just finish in another 3 minutes this sort of blah blah?
Yeah, you can finish.
Okay, so let me finish, and then if you guys want a break, I can have a break. If you guys don't want a break, I'm also fine with that. Okay, fine. Okay, so this is maybe I should pause since I said a lot of things which are non-trivial. Are there any questions about what I said?
So ADS-CFT correspondence is derived.
Sorry, I cannot hear you. I cannot hear you. Can you speak
Hello.
up? Yes.
Am I audible? Yeah. So the ADS-CFT correspondence is derived from string theory. So do we have similarly DS or flat CFT from string theory?
Do we have similarly what?
DS or flat CFT, the other solutions of the Einstein equations?
No, very much no. So for de Sitter, it's worse than for flat, in the sense that flat space at least exists in string theory. De Sitter backgrounds have been notoriously hard to construct inside string theory, and people, spent a lot of effort, and they're always unstable and whatever. Yeah, so the answer is very much no. What people do in those cases, they try various bottom-up. So yeah, so sorry, I can say maybe a few things. One thing that you can try to do in the case of flat space, you can try to take the flat space limit of ADS-CFT. Okay, so I was showing you some relationship between the size of ADS, so you have this correspondence between super young means and type 2b. This type 2b, so both the hyperbolic space, the ADS5 and ADS5 have some finite radius, which depends on the Toft coupling, as I was showing you. Of the gauge theory, you can try to take a limit where you send that radius to infinity. One thing that I would like you to note is that if you're trying to decompactify the ADS5 to get flat space, you're also going to decompactify the S5. So you're not going to get 5-dimensional flat space, you're going to get 10-dimensional flat space. And people try to write down that limit in the CFT, but it's not a Toft limit. The Toft limit is sort of a nice limit. Toft limit is n to infinity with this lambda that I was writing down, g and mu squared n fixed, which has a nice string-like expansion. That limit is something else, and I think people don't understand it very much. So people have tried to do that. Then there's a lot of bottom-up approaches to flat space holography, but these approaches make a lot of assumptions, which is not clear whether they are justified. One thing that's really missing in the case of flat space is that, so I really try to emphasize in this discussion the importance of the decoupling limit. So you start with these D branes in flat space, they're coupled to the 10-dimensional fields in complicated way, but when you take this low energy decoupling limit, they actually stop talking to the bulk. That's really, really important in deriving the correspondence. And for flat space, you simply don't have that. So to me personally, this might be just a personal opinion that's not shared by the rest of the community, but to me personally, it's not clear whether a decoupling limit for flat space exists that would allow you to write a holographic correspondence in terms of, gravity in flat space that can be rewritten as a theory without gravity that lives somewhere. So to me, that's not clear. That's flat space. I think the sitter is very, very, very confusing. People have discussed whether they should have some sort of meta observer that sees the whole time, time like infinity, or maybe it should be related to some word line observer, or there are many proposals. I don't think they've come to a common ground. So yeah, I think the sitter is even further from a realization than flat space. And of course, this makes things very interesting because we live in a cosmology that's going to become, the sitter in the far future, and we really, really don't understand the holographic principle. So I think it's food for thought. Okay, sorry. Any other question about maybe more concretely about what was it clear what I said?
Excuse me, I have another question. Can you listen to me? Just right? Okay. I'm not sure if I could understand this part in which it's mentioned that the super Young-Mills theory is an SUN. Because when I studied Young-Mills theory, the normal, it was an SUM to describe maybe electromagnetic theories with n equals 1, for example, right? SU1
yeah, so
to
the
describe.
theory on a single brain, the theory on a single D brain is U1. However, when you take these D brains and put them on top of each other, exactly on top of each other, then the gauge symmetry gets enhanced to and that you can understand it from the string theory description. So if you open up Polchinski and try to understand, how to describe this open strings. So these D brains are basically open strings with mixed Dirichlet and Neumann boundary conditions. Then you see that basically when the D brains are on top of each other, you get sort of extra massless states, which are going to make up this whole n-bind matrix of it's a language.
Okay, so that means
yeah, sorry.
So maybe when n is greater than 1 or too much, so that means there exists fields of Young-Mills from Young-Mills who are not knowledge or are not known, for example. I don't know, because the only theories that I'll studied are, for example, SU2 or until SU3 theories. But for example, I don't know what an SU100 could mean, for example.
Sorry. So this, yeah, of course. So this is something that the one standardly does in. You can consider Young-Mills theory with different gauge groups, right? So instead of doing SU2 or SU3, you can consider arbitrary n. And sort of it works very similarly with how SU2 and SU3 work. So now, right, you have these matrices and the gauge transformation, right? You have to multiply by these unitaries. It's very similar to SU2 or SU3. You just use n by n matrices instead of 2 by 2 or 3 by 3. It's totally standard. As Toft showed I think in the 70s, it's an interesting thing to do to consider the large n limit of SUN because the theory simplifies quite a lot. It doesn't simplify enough to be solvable, but it still simplifies, and he talked about these planar limits and so on, which are actually quite relevant in this study. But if I understand correctly, if your question is whether can you easily generalize the SU2, SU3 Young-Mills to SUN, the answer is yes. It's directly analogous, and this theory is actually more complicated than that because you also have fermions, you also have some particular coupling, commutator coupling, and so on. It's a very particular theory that's has maximal supersymmetry and so on. So it's a complicated theory, but roughly speaking, fundamentally it's an SUN Young-Mills theory.
Okay, thank you.
And the reason you get it in string theory, you really need to take a string theory course to understand why it appears in these three brains. It's all explained very beautifully in Polchinski's book, for example. Any other questions? Like, is anybody confused, badly confused about what I said? Let me just ask any emergency questions. So that's great. Nobody's badly confused. Okay. So I said all of this. Okay. So one of the things that I wanted to say was this strong weak business. It's really important. Otherwise, I don't think anybody would understand how a theory of gravity can be the same as a theory without gravity in much lower dimension. The second point that I wanted to mention is the so-called UV-IR correspondence. So what is this UV-IR business? And then I'll... So let me write for you the ADS metric. So ds squared ADS is r squared. So that metric in the r goes to 0 limit minus dt squared plus dx squared. So these are the directions along the brane plus dr squared over r squared. I've been absorbing some constants. And okay, so I mentioned to you that from the point of view of quantum gravity and so on, you want to think about this radial direction in ADS. So the CFT, you see, just lives in this. These are 3 dimensions. The CFT sort of lives in the TX coordinates, and the radial direction of ADS, as well as the whole sphere, are supposed to be somehow emergent from it. And you can ask yourself, what's the meaning of this radial direction from the point of view of the CFT? And sort of traditionally, this direction was identified with an energy scale in the CFT. So basically, I'm having this ADS throat. R goes to infinity, sort of near the boundary. But here, R goes to 0 is sort of in the deep interior. Okay. And to see this, so for example, if I want to look at the size in field theory, in CFT, so in these coordinates, well, the size, as I said, the CFT just lives in t and x, so it's just given by the modulus of dx. But you can easily see from this metric that this is the proper size in ADS, which is r times dx, because I'm measuring in this metric, divided by r. Okay, so if I take the same object, I don't know, a pen, and I move it from, you know, the interior to the boundary, its size is going to go to 0 as I'm taking r goes to infinity. Okay, so r goes to infinity actually corresponds to distances shrinking to 0 in the CFT. So it's the UV. So this is the IR of the space-time. The large distance in the space-time actually corresponds to the UV of the CFT, where sizes are going to 0. Also, if you look at energies, so the CFT energy is measured in this unit, so it's measured with respect to this vector dt. And as you know, in the space-time, you have the proper energy times square root of minus gdt is constant. Okay, so it's as a function of r. So you see the CFT energy is basically going to be equal to the proper energy, formally speaking, equal to the proper energy when r is equal to 1, because then I just get dt. So I get that E in the CFT is equal to E of r times r. Okay, so if I consider the sort of the same object in the bulk at different radial distances, the CFT energy is going to go to infinity when R is going to infinity. So I'm coming to the same conclusion that you cannot see, that large distances in ADS corresponds to the UV of the CFT, and I can do also the inverse statement, which is going to the interior of ADS, going towards R goes to 0, means going to the IR of the CFT. Okay, so it's opposite in the bulk, in the ADS bulk versus the CFT boundary. This is called the UV-IR connection. It also shows you that the radial direction in the bulk really corresponds to an energy scale in the CFT in this sense. So I'm always going to call this UV and this IR, although I understand that to people who didn't live in ADS CFT, this may look weird. Okay, very good. So if you guys want, we can take a break now, because now I'm going to go into more, a little bit more technical things. So we can either take a break or I can go on. Since I only have half an hour more, it's up to you.
Yeah, we can take a break, a short break now.
Okay, is 5 minutes okay?
Yes.
Okay. Okay, so
this meeting is being recorded.
So as I was saying, it's the reason that people love ADS-CFT is that it can be formulated precisely and it can be precisely tested, so it's actually useful and non-trivial. Zillions of really non-trivial checks of the correspondence. So some things that you can check, which we're going to do shortly, are the symmetries. So if two things are the same, it should better be that the symmetries on the two sides are the same. You can check the Hilbert spaces are the same. Okay, beyond these very basic things, you immediately see that you need a dictionary if you want to match things of the two sides. And the dictionary is, well, I've written it on the board. It says that the partition function of the bulk theory, so that's the ADS theory, which is a function of the boundary conditions for the fields that you have in the theory, metric, whatever other fields that you have zillions of fields actually, is the same as the partition function of the CFT, or the boundary theory, whatever it is, as a function of the sources for the various operators in this theory. Yeah, maybe I should be a bit more precise. This type of correspondence is actually supposed to be valid generally in holography, and then you can particularize it to ADS-CFT, and then you can really make sense of it. But this is supposed to be the general proposal. Well, at least when you understand what you're talking about. Now, so what I mean by Z bulk, so the bulk theory is a theory of, in principle, of quantum gravity, and in a gravitational theory on some manifold M, it doesn't make sense to fix the metric on M. Instead, since because the metric is supposed to be able to fluctuate, so the only thing that it makes sense to fix are the boundary conditions on the metric at M, only the asymptotic structure of the spacetime if you want. And for the rest, you can consider different configurations. You can also consider configurations of different topologies. That's actually a lot of fun in ADS-CFT to see this topology change and so on. Okay, so what I mean by Z bulk is the partition function for the gravitational theory with fixed boundary conditions at the boundary of, in this case, ADS5 times S5 or whatever the bulk is. But you're not fixing the metric in the interior. Okay, very good. So this is the dictionary. we're going to discuss it in a sequel. But just to start, I wanted to do the most basic thing that one can possibly match in this correspondence, in this ADS-CFT correspondence, which is matching the symmetries. So I want to match the symmetries of ADS with the symmetries of CFT. And even here, there are two discussions that one can have. So what people normally do when they talk about matching the symmetries in ADS-CFT, they talk about the symmetries of the vacuum state Okay, so these are the symmetries of a particular, the ground state of your theory, which map to isometries of empty ADS. Okay, do you see the empty? Yeah. However, these are just the symmetries of a state. And if you are really trying to match the symmetries of the two theories, they actually have there's a different correspondence that one should check. So if one tries to do the symmetries of the theory, then this actually map to what's called asymptotic symmetries. Symmetries of asymptotically ADS spacetimes. Okay, so you see the distinction. Of course, when you do whatever theory in lab, there's a difference between checking some symmetries of a particular state in the theory versus checking the symmetries of the action. This is the distinction that I'm talking about. And in the particular case of three-dimensional gravity that we're going to be discussing eventually, there's a big difference between these two. This one is infinite dimensional, this one is finite dimensional, this one is six-dimensional. Okay, so we're going to discuss asymptotic symmetries later. Now I'm going to just show you that the isometries of the vacuum map to the symmetries of the corresponding state in the CFT. Okay, so I'm going to start the discussion by telling you what are empty. Yeah, and since it's the symmetry of a, just to complete this sentence, since we're talking about symmetries of a theory of the action, it doesn't matter in what state I am. Okay, so different states correspond to different asymptotically anti-de Sitter geometries. As I explained, I'm just fixing the boundary conditions, but I'm letting the thing eventually fluctuate in the interior. These are different states. So this is why I'm looking at asymptotic symmetries of spacetimes that only approach ADS asymptotically, but they're not exactly ADS everywhere. So is the distinction clear?
Yeah, it is.
No, for
Okay,
me, no. I have a question with that. It is not clear for me the difference. I've always been confused regarding what kind of symmetry maps to the boundaries, the asymptotic one or just the isometry. Sorry, it's basically the same that you are saying, but can you repeat it again, please? Because I've always been confused with that point, please.
So I'm going to discuss asymptotic symmetries later to explain to you what they are. But if you just think in quantum mechanics, there's a big difference between the symmetries of your action, which are symmetries of the theory, and the symmetries of some particular state. Just, or to take the real world, the standard model Lagrangian is Lorentz invariant. However, the world around us, the state that we're in, is definitely not Lorentz invariant.
Okay.
That's the difference. So when I'm saying when people are checking, they look at the isometries of the empty ADS. Empty ADS is sort of the vacuum of the theory. It's the vacuum geometry. They're looking at the isometries of a state, the symmetries of the state. which are not the same as the symmetries of the theory, which are there irrespectively of the state. In the same sense that the standard model Lagrangian is Lorentz invariant no matter in what state you've decided to put your fields.
Okay, okay, thanks.
Okay, good. Good. So, but now I'm going to just be dealing with isometries because I presume that you guys don't know what anti-de Sitter spacetimes are. Am I correct?
As
Or
for
you've done
myself,
them
I know that, but maybe the
but
other.
did you do them in the course?
Yes.
You did do anti-de Sitter in the course?
Yes, yes. As for me, yes,
Oh.
but I don't know. I don't know the rest.
Okay, so what should I do? So Daniel, are you around? Okay, I guess he's not around. Okay. Is there anybody who doesn't know what anti-de Sitter spacetimes are?
I only studied this in general relativity, but not in other topics.
Sorry, you're saying no or yes? Sorry, I couldn't hear very well.
I guess not completely.
No. Okay. Okay, so let me say a few words, and okay, people who know, they're going to be a bit bored, but such is life. So anti-de Sitter spacetimes. So we're going to look, this is the standard notation, ADS in d+1 dimensions, because little d is usually the boundary dimension, the bulk is one higher dimensional. So these are maximally symmetric spacetimes of constant negative curvature. Because they're maximally symmetric, their Riemann tensor can be entirely written in terms of the matrix. So R mu rho sigma is -1 over L squared, G mu rho, G mu sigma minus G mu sigma, G mu rho. Because they're maximally symmetric, so they have maximal possible number of killing vectors in that dimension, which are basically d+1 times d+2 over 2. And then, okay, once you have the metric, you can just find all those killing vectors and compute their Lie brackets to find the symmetry algebra associated. And it is, so isometry group SO d, so this is just from the algebra of the killing vectors. And this is for Lorentzian ADS. For Euclidean ADS, it's going to be SO d+1, 1, but we won't talk about it so much. If you want to, sort of the simplest way to construct a metric on this anti-de Sitter spacetime is to actually embed it. So to construct, you do the embedding into one higher dimensional spacetime with 2 times. So these spatial dimensions and 2 time dimensions with the metric ds squared is eta tilde mn dxm dxn, where this eta tilde is -1 plus d times and then a minus over here. Okay. So you take this one higher dimension, so d+2 dimensional space time with 2 times, and then you restrict, which has inbuilt this SOD, 2. So you see this this thing is this eta tilde is basically the matrix that's left invariant. So SOD, 2 is group element transpose times d theta tilde and group element equals theta tilde. And then you restrict to the hyperboloid eta tilde mn xm xn equals minus L squared. Okay, so you see the entire construction, both this is a tilde and the restriction is SOD, 2 invariant because eta tilde had that symmetry. So obviously what you're going to get is going to have this isometry, which is what we wanted. Okay, let me also make a drawing. So I guess I can make my drawing over here. So so let me take this to be sort of the, so if I call this x0, and I call this x d plus 1, so these are the two time directions. So this goes along the sort of resulting time direction, say x0 squared plus xd plus 1 squared. Okay, and these are the some of the other xi, and here I'm drawing some sort of light cone. Then the hyperboloid, which is in time, looks something like this. Okay, so this is given by x squared equals minus L squared. Okay, but because I have 2 times, there's actually a U1 of rotations that goes so you're really getting the back of my pink. You're really getting something that looks like this. Okay, where this is basically the U1 that acts as U1 rotation in between the 2 minus directions. Okay, is the construction roughly clear? So I'm constructing a hyperboloid. If I had a single time direction, it would be very, very clear. Now I have 2 time directions, so I'm really getting an extra U1 that acts in that sort of closed timeline curve. Okay, and sorry. And if I want to, get a coordinate system along the seater, if I want to get a coordinate system on the de Sitter, well, basically I just need to, write the embedding explicitly and explicitly solve for this constraint over here. Okay, so one very nice embedding that one can, so one embedding that gives you some very nice set of coordinates, which are known as global coordinates. Is given by x0 is L cos rho cosine tau, xd plus 1 is L cos rho sin tau, and the xi are L sin rho omega I, where this omega I sum squared is equal to 1 from 1 to d. Okay, so you can easily check that x0 squared plus x d minus 1 d plus 1 squared. So this is L squared cos squared. So this comes with a minus sign. So minus L squared cos squared plus L squared c squared is minus L squared. Satisfied this. this constraint. So this is a nice embedding. And then if you want to find the induced metric on the hyperboloid, that is the induced ADS metric, basically you just take these expressions and you just plug them into the Minkowski metric over here. Okay? Some terms are going to cancel, and you're going to be left with a D plus 1 dimensional metric. Okay, and this D plus 1 dimensional metric is very simple. Is ds squared is s squared minus first squared of rho tau squared, fantastic, plus p rho squared plus h squared of rho d omega squared d minus 1. Okay, this is the metric on a d minus 1 dimensions. Okay, and this makes SOD invariance manifest. Of course, this tau coordinate that I'm writing over here is the original U1 coordinate that goes along the closed timeline curve. So the as I was explaining, the hyperboloid in the Minkowski space with 2 times actually has closed timeline curves, but that space-time has closed timeline curves, but here I can easily just decompactify that tau coordinate, and the ADS doesn't have any problem. Okay, so this is what I have to do. And you guys told me that you did Penrose diagrams. So now if I want to represent this space-time, then I can try to represent it via Penrose diagram. Okay, so how should I say? This space-time is non-compact, as you can see, because rho is going between 0 and infinity. Okay. So in order to represent it, I can try to write down a Penrose diagram. In order to do that, I should make it so that I should be changing to some coordinates whose ranges are compact, and so that I can easily do for the rho coordinate. I can just introduce. I can just say that cos rho. I can write it as 1 over cosine theta. So this goes between where theta goes between 0 and pi over 2. Okay, you see. So theta equal to 0, cosine is 1, so rho is 0, and theta is pi over 2. This is going to infinity, it's rho going to infinity. Okay, so I can make this change of coordinates, and somehow I'm not organizing my board very well. I'm sorry about that. So let me erase this. So when I do that, the metric, I can just change rho with theta in the metric, and what I get, it's a trivial exercise, s squared over cos squared of theta minus the tau squared plus the theta squared plus sine squared of theta, and the metric on a d minus 1 sphere. Okay? Very good. Where now you see that basically what's happening, okay, let's forget about tau being non-compact, but the theta is a compact coordinate, and then all the infinities that I had before in the metric are just collected into an infinity. So as theta is going to pi over 2, which corresponded before to rho going to infinity, the infinity of my spacetime. Now all that infinity is an overall factor in my metric. And somehow the whole point of Penrose diagrams and so on is that I can concentrate on the divergences in a conformal factor, and then I throw it away, and I just draw the conformal related spacetime, which does fit on the finite piece of space. Very good. So I'm supposed to not care about this prefactor because I'm going to the Penrose diagram, which doesn't care about the conformal prefactor. question, what is this part of the space? What is it, the metric on? Where theta goes between 0 and pi over 2.
Here.
I couldn't hear you.
I'm sorry, a sphere.
Like the S-sphere. So the D.
It's a sphere in how many dimensions? If this was d minus 1, it's going to be a d-dimensional sphere. Is it an entire sphere?
No, it's just a section of it.
Yeah, it's going to be half a sphere because on a proper sphere, theta goes between 0 and pi. Whereas for me, theta only goes from 0 to pi over 2, so I'm only getting half a sphere, which is the same as a disk, topologically speaking. Okay? So basically what I'm going to get is a drawing like this. So actually, for the purposes of ADS, people usually don't care about the fact that tau is non-compact. Some people do, and then they make it, cusp like this. But okay, let's forget about it. So I'm still going to keep tau non-compact, and then I have this sphere. So theta equal to 0 over here, theta equals to pi over 2 at the boundary. Okay, and this is a disk, which is the same as half of this SD. Okay, so this is the theta course. Okay, and so now, okay, so I have this conformally related metric. The conformal boundary of the ADS spacetime is basically the boundary of this sort of finite manifold, which is without the conformal factor, and the boundary of this finite manifold is what? Well, the boundary of this manifold, I'm just taking theta going to pi over 2, so it's going to be r around tau, because it's still infinite along this direction, times n is d minus 1. Are people happy with this? So the boundary, so this is like a cylinder. So I argue this half of a sphere is the same as a disk. The disk times the line is a cylinder, a filled cylinder, and the boundary of the filled cylinder is the empty cylinder, but it's just that it's d-dimensional. Is this okay?
Yeah, that's more
okay.
clear. Thank you.
It's okay.
Okay. Okay, so this is the Penrose diagram for anti-de Sitter, and from it you can see a lot of like cute things about its behavior. So just in terms of time, I think what I'll have time to do, I'm just going to finish this ADS part, then follow CFT, but I guess I'll have to do that next time. Daniel or whoever's in charge, do you agree with this? Since I don't want
This meeting is being recorded.
Okay, very good. So, okay, so now that you have the Penrose diagram, so the great usefulness of Penrose diagrams that you've learned about is that you can easily see the trajectories of light rays, which travel at 45 degrees. And one thing you should be able to see very easily is that if you shoot a light ray, let me make it yellowish, towards the boundary, it reaches the boundary of ADS in finite coordinate times. And can you guys tell me how long does it take a light ray shot from here to reach the boundary? Just to help you, so I'm assuming that the light ray is sent radially, okay? And this is the metric. question being, how much coordinate time does it take for a light ray to go from the center of ADS, which is at theta equal to 0, to the boundary of ADS, which is at theta equal to pi over 2.
Maybe proportional to L.
It's also proportional to L. So I'm setting L to 1 for now. Yeah, you're right. There's a factor of L. But if L equal to 1, then what's the time?
Sorry,
Okay,
here
so
radially means along the theta
yeah, along a
direction,
constant
right?
angle, which means that that I don't care about this part of the metric because it's staying at the constant angle, so the omega is 0. So I only need to look at this part of the metric in order to see the trajectory.
I mean, if you go to theta to pi halves, shouldn't, I mean,
Exactly.
for this count,
Yeah,
we are, yeah, no, for this count, we are considering the prefactor outside.
Yeah, so no, yeah, because you don't care about the prefactor outside, right? Because you're just setting the squared equal to 0. But then, of course, this is dimensionless and this should be dimensionful, so there should have been a factor of L here, really, for dimensional reasons, but I put it to 1. So you see, indeed, the trajectory of the light ray is going to be, you know, tau equals theta, and theta is going from 0 to pi over 2, so delta tau is going to be pi over 2.
Okay.
So it takes, yeah. So going from here to here is going to be pi over 2. So, you know, to go and bounce back is going to, yeah, it's going to take pi times LADS, because really I should be measuring time in ADS units. Okay, so this is a very funny feature of anti-de Sitter spacetime. It clearly doesn't happen in flat space. If in flat space you send a light ray to infinity, it's just gonna go to infinity and never come back. In ADS, if you put the reflecting boundary conditions at the boundary, which are very natural in ADS, it comes back in finite coordinate time, in like one ADS. And this is despite the fact that the radial distance to ADS, which is measured in the full physical metric, is actually infinite, right? This boundary is at infinite, you know, coordinate distance away in the physical metric. But light rays take a finite time to come back. Okay, so these are light rays. One can also look at massive particles, which go along time like geodesics. And, you know, I don't have time to derive it, but actually I'm going to put my notes up so you can see the calculation or you can do it yourself. Actually, massive particles never reach the boundary. So they sort of bounce back and forth over here. Okay, so and you can show that, you know, okay, so if, with more energy that you send them into the boundary, the farther out they reach, but they never reach the boundary. So it's somehow very, very natural in ADS to put Dirichlet boundary conditions for the fields because okay, anyways, these guys are reflected at the boundary in the classical limit. Okay, so it is basically acts as a confining box for massive particles, which is very nice. The last thing that I wanted to say about ADS, so these are global coordinates which cover the entire space-time. Another set of coordinates that people like to use are the so-called, write it here, Poincaré coordinates. And okay, you can either look at my notes or Madasena, or okay, this is super standard. So Poincaré coordinates on ADS, you can do a slightly different embedding, and they look something like this: eta mu nu, dx mu plus dz squared over z squared. So now z is the radial coordinate. Z goes to 0 is the conformal boundary. And these are basically the boundary coordinates, which make sort of evident the fact that the boundary is Lorentz or Poincare invariant. So these coordinates are sometimes much easier to use than the global coordinates. This is why people use them. However, they only cover a part of the ADS spacetime. So actually they only cover, and I always have problems. So they only cover a diamond, a piece of the ADS spacetime. So how am I going to do this? I'm going to do this like that. Okay. So Poincare coordinates that I've written over there, they only cover part of the ADS spacetime, and this part looks like a diamond on the boundary. So if I unfold the boundary cylinder, the Poincare coordinates cover a diamond of that cylinder, and in the bulk, okay, it's the bulk you know. So that's another important set of coordinates on anti-de Sitter spacetimes. And so far, okay, what can I say? This different coordinate system make obvious different isometries of ADS. So as I was saying, here it's very easy to see Lorentz. You can also see the translation in the axis very easily. And you can also see scaling. So if you rescale Z by a constant and the X mu's by the same constant, you obviously need the netting invariant, so they make a certain dilatation symmetry in these coordinates evident, which is going to be useful later when we compare to CT. Okay, so what I presented so far were the isometries of empty ADS. So as I explained, these are the symmetries of the vacuum solution. And next time, I'm going to talk about what are CFTs, what symmetries they have, and we're going to say that this match to the symmetries of the CFT, in particular the symmetries of the vacuum solution. Okay? So with that, I end for today, and please let me know if there are any questions.